Johnson.
And I'm Austin Dyer. All right, we wanted to create a Bosun's Chair 5000. We came up with the name Bosun's Chair 5000. Our original idea was to come up with a way to attach to the side of a ship as a Bosun's chair does, except we would have magnetics instead of welding points on the ship. So we went about trying to do calculations and stuff like that. We started out with the initial testing with the microwave transformer, as you can see here, and then Austin can go into some of the other details of what happened from there.
So with the microwave transformer, we were met with a lot of constraints that simply we could not change with our stock electromagnetic or microwave transformer. So what we decided to do was build our own. So we managed to get a hold of some 4-inch stock, and we went through the process of cutting it, milling it, cleaning it up, making sure it looked good and it met our specifications. But we were met with the idea that because an electromagnet has coils, and we need to fit a certain amount of coils inside of our electromagnet. This means we had to work with the area that we had and think of a way to maximize the amount of surface area we had with the electromagnet and the amount of turns and coils we could fit inside the electromagnet.
So this is the microwave transformer version, and this is your new, polished, beautiful, sexy version. Yes. All right.
So we had to make our spools out of a 3D plastic. So we went into SolidWorks on the computer. It's a CAD type program, and designed the spools to these dimensions here.
So it fits in perfectly.
Yes, and you can see that it is, as Dr. King pointed out, it fits perfectly.
You can see in the schematics here for those.
That's hot.
So after making the spools, we had to go through and put on our 20 gauge magnetic wire. And this wire was wrapped around many times on the lathe, which took a little while. But we managed to fit about 1,300 turns onto the spool. And that's for each magnet, because we have 2 electromagnets. And then after putting the wire on, we did all our wiring, hooked up a switch so we could disconnect the current for moving it along our surface, kind of like monkey bars.
So is this going to stick to something?
Yes.
Yeah?
Stick to some metal.
Can we see something stick?
They're all geared up.
Sure.
I think we should.
Yeah, well, we have a little demonstration to show you.
We'll start out with our demonstration
Oh, the
first.
demo. Okay, all right. Okay, so I hold this. Okay, so I put this on the metal.
So we're going to start off first on the thin steel, the quarter inch.
Steel.
We're going to put 12 volts to that.
Just 12 volts.
Just 12 volts. So we're going to see if you can pull it off.
Okay, I'm ready. Okay, is that 12 volts? Okay, all right, not so bad, not so bad.
So
Yeah, I've been working out.
to 24 volts.
Okay,
See if
20.
Dr. Chang, see if you can get that.
24 now?
24.
Okay, I'm ready.
A little harder.
Oh, okay.
There you go.
Oh, yeah.
Okay, 36. Let's see if you can do it.
Okay, all right, all right. Okay.
They teased me about the gym. Can you believe that?
Oh, okay.
All right.
I got it.
36.
I got some guns.
So that same voltage, we're going to try that now on that inch thick steel.
Okay.
So this is going to be 12 volts.
Okay.
Start out.
12 volts, 12 volts, inch thick.
Inch thick.
Okay. Okay. Hold on. I got to make sure my bat. Oh, okay. That was much
12
harder.
volts, you got it.
A little harder.
That was a little harder.
Okay, 24.
Apparently, you want to
Okay.
throw your back out?
Okay, ready? I got to keep the back straight, right?
Yeah,
back
back
straight.
straight.
Back straight. Like a deadlift. Oh my God. Oh.
Okay.
Okay.
So as you can see, it was a lot harder for him to lift that magnet off of the inch thick steel. And if you look over here, you can see we did some finite element analysis where we modeled with a mesh analysis. We modeled with the type of steel, the air. We set a boundary layer to that. We did the type of wire that we used to wrap, which is 20 AWG magnet wire, 1,350 wraps. And then from this model, we were able to basically do a calculation.
643 newtons of force.
Yeah. So when this magnet, this is a cross section.
What does the yellow versus the purple mean?
So the yellow is about halfway of. This is all with B with our Tesla field.
Yep.
So this is flux density. So blue, like the outside would be like 0, and purple is going to be the most. It's like around 2, I think. And so if you look, you can see when it's up to the 1/4-inch steel, this is a cross section of our magnet, it's really oversaturated with the B field, so you have a lot of leakage. All this green is, again, it's Tesla that's leaking out, and this line is showing Tesla, it's leaking out. So that's why it's so easy to pull that off. And if you look down now at a 1/2-inch thick steel, you can see that all the lines stay within the magnet itself, so you're getting the full force, or the force ability that it would have. So at a 1/2-inch steel, you can get 1,708 newtons of force with we did an integration of that surface, and with the 1/4-inch, you were only able to get 600 newtons of force. So huge difference, 600 to 1,700 newtons of force. So the 1,700 is about 380 pounds.
So I think I need to bulk up.
So again, that's a cross section of this magnet.
Okay.
So
So why do you got all this?
Why do you have
gear?
all this gear
Yeah,
on?
why do you have all this gear?
well, we're gonna test it out.
Oh, cool. And what kind of power source do you have there?
This is a 12 volt LiPo battery. These are normally used for quadcopters. So this actually can run off double A's, but since I'm going to be hanging on it, more voltage means more amps, so it's going to be a stronger magnet.
So that's just in case it does come off, which it's not. But
Yeah, this is just so that if it does,
you got your helmet on. Okay.
the rope is for if the line came off that Austin has it. And then these are called aiders. And I can rest my legs or my body weight on my legs. So really the only thing that will be holding me up is going to be the magnetic force on the bottom of these.
Okay. What is it? On belay? Belay on? Is that?
Yeah, it is.
Yeah. Did I get it right? Yeah. I've done some rock climbing. All right. Oh my God. Oh, we got the ladders attached to that.
This is the aiders, so I can rest. Okay, fire her up.
Is this really happening? Is this really happening? Yeah. It's not coming off, huh?
So one is the energizer right now.
Wow.
So all the weight can be held with one.
Just one. Yeah.
Some problems that we've been running into is not a fully flat machine surface will really affect it. We'll have an air gap in there, things like that. Yeah. I mean, he's good. I trust him. Yeah.
Cool. All right, we'll let him down. So put him down. Make sure he gets down. We'll have video evidence that he gets down in one piece. All right, guys, challenges. Talk to me about challenges.
First of all, we have some challenges with the equations. So it's hard to find the equations that we really needed.
Yeah.
And,
A lot of nonlinearity.
Yeah, a lot of nonlinearity.
Yeah, sensitivity to the thickness, sensitivity to what material, sensitivity to the air gap. So much stuff that so many things that the equations don't necessarily capture. Yeah.
Yeah, it was definitely harder. Yeah, it was just an interesting thing because to machine something like this, you have a lot of real engineering constraints. You know, we were constrained by how much weight could I actually be lifting with my arms, how much area can we even get. You know, a 4-inch piece of steel was big. Like that was really hard for us to even find. So we were constrained with that area, and then we were constrained with how many turns we could get. And the amount of turns and the amount of amps are things that increase your magnetic field, but at a certain point you're limited by them because if you have thin gauge wire, you're going to melt your wire if you have high amps. So there's a lot of different battery types, different considerations. So it was a real engineering problem.
On top of that, I mean, the amount of time it took just to machine that piece of steel with that much material, it was about 20 hours just of machining per electromagnet.
Oh man.
So it was a lot of time just to get it, you know,
And
cut
you
down.
still got the notes rewritten.
Yeah, still rewrote. Yeah,
Still
all the
rewrote
notes.
the notes. Look at this guy.
A plus.
Look at this guy. Advice to the new incoming seniors.
Start early.
Yeah.
Have a clear and decisive plan. Do a lot of testing prior to. Don't try to go big the first time out.
Yeah.
Small scale testing is the best thing. With ours, we cut. I think I ended up cutting 4 or 5 transformers apart.
Yeah.
We started with the smallest one first and tried to get testing done that way.
Yeah.
And that's probably the biggest.
Yeah, you're gonna run into hurdles and roadblocks along the way. You don't know certain things, so if you start out small and like look for the mistakes before you get too deep in the problems. And another thing would be just communication with the team. You know, making sure you're all in the same playing field, that you're all motivated the same, that you all have the same drive to do. You know, this is a big involved project. So if people weren't involved, it wouldn't have happened. So
You know what I liked? I like that you bit off a chunk, both theoretical and practical. Theoretical, practical. You marched along. You didn't just go completely practical or completely
and it's swapped between the two,
Right.
because we started out with theoretical with calculations.
Yeah.
When those weren't working, we had to just try things.
Yeah.
We just had to see what worked physically and understand that, you know, maybe we weren't able to measure the amount of Tesla we were getting. So it's probably there, but we can't tell. And then eventually I figured out the modeling, which actually that hit on the head how much weight we can lift with this. You know, we tested it to lift 340 pounds with, you know, like, and this calculation shows 380.
And I think that leakage is huge because we saw minuscule Tesla when there's no plate. And then when we put that plate on, that Tesla just jumped up, right? And that's a huge lesson. So, thank you so much.
Thank you.
Jackin, you guys melt my heart. So good. So proud of these guys. Can't say enough. Can't say thank you. All right. Really, you guys put in the effort. I think I want to cry. Okay.